in today's lecture, we will start from where we left in the last lecture and then we will continue. So, in the last lecture, we have learned the concepts of chords, we have learned all of them. Also, we have learned the basics of diameter. So, when it comes to diameter, if slope of chords is given as m, we can get the equation of diameter. This we derived in the last lecture. Equation came out to be y equal to bx by am, b square x by a square m. And we have also concluded that every line that is passing through center is a diameter except the asymptotes, and every diameter passes through the center. Now, we have also understood these geometrically. So, let us move on to the next concept, which is the conjugate diameters. Now, you know the definition of conjugate diameters from ellipse. Same concept can be used here and conjugate diameters can be understood. So, that means what happens is chords corresponding to one diameter are parallel to the other diameter, and chords corresponding to this second diameter are parallel to the first diameter. So, in that case, the condition between slopes must be m1 m2 equal to b square by a square. Now, if you recall the condition of conjugate diameters of ellipse, for ellipse it was m1 m2 equal to minus b square by a square. So, here you can straight away understand that in ellipse, if it is this, then in place of b square, if I put minus b square, I can get the condition for conjugate diameters of hyperbola. So, ellipse and hyperbola are always connected. As I keep saying, ellipse and hyperbola are cousins. Most of the properties also will remain same in both these curves. Okay. So, this way we can understand all diameters and conjugate diameters and we can just close it. So, diameter itself is a borderline concept. So, conjugate diameters is definitely out of the boundary concept. So, it is not in the syllabus, but still we have discussed it. Now, can we move on? So, here are some properties that are better to be remembered, but these are easy properties only. For example, if you look at the first one, locus of the foot of perpendicular from foci to any tangent is going to be auxiliary circle. It is the same property that was defined for ellipse also. Next, product of perpendiculars from foci on any tangent is b square. So, this property is also same as ellipse. So, if we learn this for ellipse, it is same for hyperbola also. Next, if PSQ is a focal chord, then 1 by SQ, 1 by P equal to 2 by semilatus rectum. This also we have learned and also we have proved. In fact, if you look at this property, it is same for parabola, ellipse and hyperbola also. For all three of them, it is the same. So, we can also say that semilatus rectum is the harmonic mean of the segments of the focal chord. Okay. Next, the area of triangle formed by any tangent with the asymptotes is always a constant, which is going to be AB. Now, this seems to be a new property. This was not there in ellipse, but it is there in hyperbola. So, we will try to prove this. Now, we are going to prove this fourth property. Suppose let us say if I take one branch of the hyperbola and let us say I have taken the asymptotes here, the equation of this asymptote is going to be y equal to b by a into x, and equation of this asymptote is going to be y equal to minus b by a into x. Now, if I take any tangent, let us say I take tangent in red color. So, if I take any tangent, this tangent intersects both asymptotes at 2 points. So, let us take them as let us say A and B. Now, we know that center is basically O or C and it is going to be origin. Center is the point where asymptotes intersect. Now, we want to prove that the area of this triangle is always constant. Now, what is the best way to do it? get the coordinates here, because we already have one coordinate which is 0, 0. Get the coordinates here and try to find the area by the determinant formula, or if you can get these coordinates A and B, you can also apply the idea of half base into height. So, it is left to you, you can do it in however way you want. I am going for half into base into height. Okay. So, if I take, let us say, tangent as x by a sec theta minus y by b tan theta is equal to 1. If I want to solve for b, I have to put y equal to minus b by a x here. If I put minus b by a x for y, what do I get for x here? So, I am basically calculating b here. So, to calculate b, I have to put y equal to minus b by x. So, it gives me x by a sec theta minus b by a into x into tan theta by b is equal to 1. So, here b gets cancelled and you are going to get x equal to a by sec theta minus tan theta. Okay. So, that is the x coordinate, and y coordinate can be directly calculated. So, I can say that b is going to be a by sec theta minus tan theta, s means sec theta, t means tan theta, and this into minus b by a will give me the y coordinate. So, that will give me minus b by s minus t. Now, same way we can also get the other one. Okay. So, here it has to be minus b by a into x, so it must be s plus t here. Okay. Now, by following the same idea, we can also get the coordinates of a. So, coordinates of a here will come out to be a by s minus t, comma b by s minus t. Okay. So, this way we can get the coordinates. Now, to find the area, we have to find OA and OB lengths. So, here if you observe what will be OA and what will be OB, you can directly substitute and simplify. So, OA is going to be root of a square plus b square by s plus t. Similarly, OB is going to be root of a square plus b square by s minus t. Now, if we simplify, if I find the area, area is going to be half into OA into OB, which is same as half into a square plus b square divided by s square minus t square. That is what we get in the denominator, and we know that sec square theta minus tan square theta is 1. So, we can say that this is going to be equal to half into a square plus b square. Now, can we get this value a square plus b square? Of course, we can, because we know that b square is going to be a square e square minus a square. So, what is this a square plus b square? It is coming out to be a square into a square, right? Okay. So, still we are not getting it. Okay. So, half into OA into OB has come out to be somewhat like this, and when we simplified here, we are not getting AB. Okay. So, let us say we do it the other way. Okay. So, let me just explain it here also using this idea. So, if I go for the coordinates, this was which one? Minus b by s plus t, right? And here a by s minus t, and here b by s minus t. Here also we can use the similar idea. Let us say if I just take the determinant of this 2 by 2 form, because already there are zeros here. So, we are going to get something like half into AB plus AB divided by s square minus t square. So, here we just got AB. Okay, so I might have done a mistake here. You please check the mistake and try to correct it. Okay. So basically here, if you understand, area found by the tangent with the asymptotes is always constant for any hyperbola. If it is rectangular hyperbola, then it will be equal to a square. If it is simple hyperbola, then it is going to be ab. Okay. So here I am skipping this because we do not have so much time, because we only have 2 lectures to complete hyperbola. We also have rectangular hyperbola to cover. Okay. So you try to prove this on your own. Okay. So this way we can prove this property. Now as I keep saying, it is essential that we prove all properties that come for any curve, because proving is not actually wasting time, proving is actually developing skill. In every proof you are actually learning a skill of problem solving, just like the way we have seen here, there is a skill of problem solving. Okay, come on, make a note of this. Okay. So can we proceed now? Okay, next. Product of perpendicular from any point on hyperbola to asymptotes is always constant and it is equal to this constant. Now how do we prove it? We use similar setup. So let us say I have taken 2 asymptotes here and I have taken one branch of hyperbola. So from one point, let us say if I draw perpendicular here and also if I draw perpendicular here, if I take this as d1 and d2, so what do we have to prove? We have to prove that d1 into d2 must be a constant. So how do we do that? Equation of this asymptote is y equal to b by a into x. We can also take this as ay minus bx equal to 0. Similarly, this asymptote can be taken as ay plus bx equal to 0. And if I take this point as, let us say, a sec theta comma b tan theta, I can straight away apply perpendicular distance and prove it. So you can just do it like this. If I put the point here, what do we get? AB into sec theta minus AB into tan theta divided by root of a square plus b square. This is the first distance. And now the second distance will be AB into s plus AB into t divided by root of a square plus b square. This is the second distance. Now if you observe, what do we get? A square into b square by a square plus b square into we get sec square theta minus tan square theta, which is going to be 1. So hence we have proved it. So all properties can be proved in a very simple manner if you hit the right node. Okay. So now next property is this, we have already learned in second lecture or third lecture. If 2 lines are given which are L1 and L2 as asymptotes, and if you are interested in finding the equation of the hyperbola, so L1 into L2 equal to constant will give you the equation of hyperbola. Now if you are interested in the conjugate, then you just have to reverse that c to minus c. This is the main idea based on which we can solve many questions. So I would say that this property is 5-star property. Okay. It's very important property, it is definitely 5-star property. Okay. Now there is next one more property. If P is a point on hyperbola, then the tangent at P bisects the angle between SP and S dash P. This we have solved as a question in tangents. So we have proved this using the property of angular bisector, which is angle bisector divides the opposite sides in the ratio of the other 2 sides. Okay. Can we proceed now? Okay. So next property, this is called as reflection property. Now what is the reflection property here? So I'll just explain it here. Suppose let us say we take an ellipse. We take an ellipse and let us say there are 2 foci here, S here, S dash here. There is a point P here and any light ray passing through S, when it gets reflected at P, the reflected ray will pass through S dash. So this means if you put one light here, if you put one light source, let's say one torchlight or anything, then all light rays that are going to generate here, they get reflected from this elliptical mirror and they all pass through the next focus. So that means the image will come at S dash. If S is the source, S dash is the image. Similarly, if S dash is the source, S will be image. Now same thing if we apply for the hyperbola. What happens here is somewhat similar but a little bit different. So let's say I have the curve here. Now if I throw a light ray here, when it gets reflected, it is going to generate one reflected ray. But the reflected ray will pass through the other focus. So that means if I join the point here, then this part and this part will lie on the same line. Now here if you notice, only difference is the direction of the light ray. So here the light ray is passing out away from the focus. Here the light ray is passing towards and through the focus, towards and also through the focus, but here it is moving away from the focus. But if you take that line, it has to pass through the other focus. Now this is, if you look at these two diagrams, there is a similarity. As I keep saying, these two are cousins. So same ideas are applied everywhere. Okay. So here the idea is same, and you can, if you understand the property of ellipse, you can also understand the property of hyperbola. Now how do we prove this? We have actually proved it in the earlier property. So that means if I take this tangent and if I prove that this angle and this angle are equal, that means I have proved that the angle bisector of PS dash and PS is basically the tangent. That means I have basically proved that this angle is equal to this angle, because if you look at these two are basically opposite angles. So if this is theta, this also must be theta. If I have proved that these two angles are equal, so I have basically proved that these two are equal. So hence relation is derived that incident angle is equal to reflected angle. So that means of course we have proved the property. Okay. So this property is basically derived from the earlier property that we have just seen here. Okay. So this is one reflection property that you can understand. So that I have put in the words, but if you understand this geometry, then everything is cleared. Now if you look at the overall picture of conics, now there is one idea that has been there in all of them, in parabola, in ellipse and also in hyperbola, which is the reflection property. So for all these three curves, there is reflection property. Now if you also try to compare this with the circle, so in circle what happens is, at the center if you put a light ray, if you put a light source, then all light rays that get generated from here also will come back to the same point. Okay, because these light rays meet the mirror at 90 degrees. So because there is only one point which is the center, we can also treat that as two foci being collapsed at one point. So that way we can understand this reflection property for all conics. Okay. Now for parabola, you can imagine that there is one focus and the other focus is at infinity. So that means all these light rays, when generated from one focus, they get reflected from the curve and they try to go through the other focus, and other focus is at infinity. So all light rays will go parallel as a beam. Okay. So that way you can connect all reflection properties of all conics, including the circle, and understand. Okay. So now can we move on to the next concept? Okay. So now let us solve some problems based on these ideas very quickly, and then we will go on to the rectangular hyperbola and we will study that in depth. So there is this first question. There is a chord PQ which subtends right angle at the center C, and we have to find the value of 1 by Cp square plus 1 by Cq square. So here so if I take one branch of hyperbola and there is a chord here. Okay, so let us say this is the chord and let us say this is the center. Now, if I take this point as, let's say, P, this point as Q, and here if I join these two, and if I take the center as C, this angle must be 90 degrees. It is given that this angle is 90 degrees, and we have to find 1 by Cp square plus 1 by Cq square. So, 1 by Cp square plus 1 by Cq square. Now, let me take you through one geometric property. In any right angle triangle, let us say if I take this length as L1, if I take this length as L2, and if I take the perpendicular drawn from the point of right angle to the hypotenuse as L, there is a standard theorem which says 1 by L1 square plus 1 by L2 square equal to 1 by L square. Just like Pythagoras theorem, you also have this standard theorem. You can try to prove it on your own. Now, using this idea, if I have one perpendicular here, so if I have one perpendicular here, let us say this is my perpendicular which is L, we can say that this length is going to be 1 by L square. Now, this is the idea on which I am going to solve the problem on. Okay. So, how do we solve this problem? I assume that the chord is y equal to mx plus c. So, here I am not going to use the parametric form of chord or any standard form of chord. I will solve this in a completely different way. If you are willing to try, you can also try it by taking P as eccentric angle alpha, Q as eccentric angle beta, and then try to generate the condition and also try to solve it. But that is left to you, it is going to be a long method. I am going to give you a better method. Suppose if I take the chord as y equal to mx plus c. So, if I take the chord as y equal to mx plus c, and the curve is x square by, what is the equation? 9 minus y square by 25 equal to 1. And I know that this line is intersecting the curve at 2 points, and I am interested in the lines which are passing through the origin and also passing through these 2 points of intersection. Now, what is the idea that is striking your mind? It is the homogenizing idea. So, basically using this equation of straight line, I am going to homogenize this curve. How do we do that? We have to generate 1 from here using the constant term. So, that means I have to keep constant in RHS, and then I have to divide with that constant and get 1 there. And whatever is the degree of this term, if you look at the degrees, so there are some terms with second degree, there could be some terms with linear degree, but linear terms are absent here. There is one term with 0 degree. Now, we cannot reduce the degree of the second degree terms, but we can increase the degree of the 0 degree terms. So, that means we will multiply 1 with this term as many times as possible, so that entire equation has a uniform degree. So, for that what do we do is, we multiply this 1 with y equal to mx by c whole square. Okay. So, by doing this I have converted the equation into a homogeneous second degree equation, and homogeneous second degree equation could represent 2 straight lines passing through origin, and here we are basically interested in these lines Cp and Cq. So, because I have used the chord and also these two, so I am assuming that I am going to get lines for sure. I am just assuming that I am going to get lines for sure. If it is the other case that we are not getting lines, then that means we are not actually solving the problem. Okay. So, here this homogeneous equation is going to represent the lines Cp and Cq. Because I want these Cp and Cq to be perpendicular, what is the condition of perpendicular pair of straight lines? Coefficient of x square plus coefficient of y square must be 0. So, here if I just add them, coefficient of x square plus coefficient of y square equal to 0, I may get some condition. Based on that condition, I will choose how to solve the problem. Even till now, I have not seen the next steps. So, I'll know the next steps, I'll know the next steps of the method only after I see these algebraic steps. Okay. So, if I get the x squares coefficient here, so from first term I am getting 1 by 9, from here I am going to get minus m square by c square, this is the coefficient of x square. Now, let me get coefficient of y square also. From here I am getting minus 1 by 25, and from here I am getting minus 1 by c square, this must be 0. Now, here if I take all parametric terms to the RHS and all constants to LHS, what do I get? 1 by 9 minus 1 by 25 is going to be equal to m square by c square plus 1 by c square. Now, if we simplify this, we are going to get m square plus 1 by c square is going to be 16 by 9 into 25. Okay. Now, I got some relation here. I'll not further simplify this. I'll see how the problem is turning out to be. Based on that, I'll decide whether to simplify it or not. Okay. So, what I'll do here is I'll try to calculate L. What is L? L is the perpendicular distance from 0, 0, that is origin, to the line. What is our line? Our line is y minus mx minus c equal to 0. This is our line. So, what will be the perpendicular distance? This L is going to be, substitute 0, 0 here, which will give me minus c divided by root of 1 plus m square. Now, because I am interested in L square, I will also square this, and because 1 by L square is required, so I will directly take 1 by L square. So, 1 by L square is going to be 1 plus m square by c square. Now, see what is the term that we got for 1 by 1 plus m square by c square, it is 16 by 9 into 25. So, we can write this as 16 by 9 into 25, and this will be our required answer. Okay. So, this way we can solve the problem using homogenizing. Okay. So, if you get any questions of this type where the chord is directly connected to the origin somehow or the other, that let us say here it is making 90 degrees, or let us say lengths are related or some other ideas, then try to take help from the homogenizing. Okay. Come on, make a note of this. Okay, next. Find the locus of midpoint of chords of circle which are tangents to hyperbola. So, here this question is one prototype of questions. So, in general two curves are given, chord of one curve is tangent to the other curve, then find the locus or find condition or some other kind of questions may come. So, in this type of questions, how to proceed? So, here we want to find the locus of midpoint. So, let us start from the midpoint. If it is some other idea, maybe we may have to start it with some other idea. So, here you need to practice this with your experience. I will discuss this after I solve the problem. Okay. So, if I take the midpoint as let us say h comma k, then equation of chord will become S1 equal to S11. That means xh plus yk minus a square equal to h square plus k square minus a square. So, if I cancel out a square, I got some term here. Okay. Now, how will the tangent look like for this curve? Tangent looks like this: x by a sec theta minus y by b tan theta is equal to 1. Now, the chord of one curve must be tangent to the other curve. So, that means these two equations must match. So, we have to compare them. So, that will give us sec theta by ah equal to minus tan theta by bk is equal to 1 by h square plus k square. Now, we want to eliminate theta from here directly. So, how do we do that? By using ideas of ratio and proportion. You know this idea. If a by b equal to c by d equal to let us say e by f, then a square plus c square by b square plus d square, this ratio is going to be same as a square minus c square by b square minus d square. which is going to be same as a by b whole square or c by d whole square, or it is also equal to e by f whole square, or it is also equal to ac by bd. So, these kind of ideas we can use whenever required in especially coordinate geometry. So, here I am just seeing it directly here, because I know that sec square theta minus tan square theta is always going to be 1. So, here I am going to apply that idea. So, what do I get? Sec square theta minus tan square theta divided by square the denominators and subtract. So, a square h square minus b square k square is equal to square of this third term, which is going to be 1 by h square plus k square whole square. Now, we know that sec square theta minus tan square theta is 1, and we are going to replace h with x, k with y. So, it is going to give us a square x square minus b square y square is equal to x plus y whole square. Okay. So, this is going to be our required locus. Okay. So, this way we can find the locus. Now, what is the discussion? Discussion is like this. So, here let us say there is curve 1 and here let us say curve 2. Now, sometimes questions may come like this. Case 1, tangent to this curve is also same as tangent to this curve. That means basically we are looking for common tangents. So, how do we proceed? Write both tangents in slope forms and equate the C. Okay. Now, questions also could be somewhat like this. Tangent to one curve is normal to other curve. Now, what is the procedure? Same procedure. Write the tangent and normal in slope forms and equate the constant term. Next, tangent to one curve could be cot to another curve. So, in this kind of situations, we have to start from the chords. Okay. So, here the logical flow must be starting from the chord. We have to first write the equation of chord, then go for the condition for tangency, or write the equation of tangent and try to compare them. So, either you go for slope form or you go for the parametric form of tangent, it is fine, but you have to start from chord. Now, similarly, based on the situation, you may have to understand some methods. This is what I keep saying, that you have to learn this by experience only. Okay. So, because I have solved many questions, I may have few ideas. Even if you also solve many questions, you also get some ideas. Okay. Now, you do not have to copy teacher, you have to also learn to develop your own methods. Okay. So, those who learn to develop their own methods crack IIT. So, that is why it is essential that you learn all proofs and also learn all methods. Okay. So, keep exploring, keep trying different methods. Of course, that experience will definitely teach you something. Okay. Come on, make a note of this. Can we now proceed to the next problem? So, the line joining these two passes through the right focus, find E. Okay. So, this is going to be very easy question. We just have to put angles and the point AE, 0 and get the value of E. Okay. So, I will just explain the steps and I will move on. So, this is our equation of chord. Now, in the last lecture, I have taught you how to remember this form. If you remember it, then you do not have to worry much about it. Okay. So, I connected chord of circle, ellipse and hyperbola. If you remember one, you will remember all. Okay. So, here we have to substitute AE, 0 and also we have to put alpha equal to pi by 3 and beta equal to minus pi by 6. So, what do we get? If I put AE, 0 here, I will get E into cos of pi by 3 plus pi by 6 divided by 2 is equal to cos of pi by 3 minus pi by 6 divided by 2. Now, pi by 3 plus pi by 6 is going to be pi by 2. So, this is going to be pi by 4. So, we can write E as, in the denominator we are going to get cos of pi by 4 and here pi by 3 minus pi by 6 is pi by 6, pi by 6 by 2 is pi by 12. So, cos of pi by 12. Now, you know that the angle pi by 12 is nothing but 15 degrees. You can write 15 degrees as 45 minus 30 or 60 minus 45, it does not matter. So, what do we get here? We will get root 3 plus 1 by 2 root 2 divided by cos of pi by 4 is 1 by root 2. So, E is going to be root 3 plus 1 by 2. Okay. So, this way we can solve this problem. I think this is very easy problem. We are straight away moving on. Okay. Okay, next, given the base and ratio of tangents of half of the base angles, show that the locus of third vertex is a hyperbola. So, here it must be a comma. Okay. So, how do we do this? So, here we have to first understand the given data. So, as I keep saying, beta, everything is about data. Okay. So, here one statement says that base is given. So, if it is read in any question that given the base, so what is given to you? What are all the data points that are given to you? One is this point is given to you. Okay. This point is fixed. Second, this point is also given to you. So, it is also fixed, and the length is also given to you. So, if I take this point as C, so this length is small c. So, this is also given, that means it is a constant. Okay. So, these three values are given in this one single phrase which says given the base. Now, next, the ratio of tangents of the half of the base angles. So, that means tan A by 2 by tan B by 2 is given as a constant k. Now, this constant must be positive constant. Why? Because if you look at the angle A and B, these are angles of triangle. So, A and B must be belonging to 0 to pi, which is 0 to 180. Half of it will be belonging to 0 to 90. So, that is first quadrant. So, tan A by 2, tan B by 2 both are positive. So, hence the ratio must be strictly positive. Okay. Now, this value of k can also be equal to 1 or greater than 1 or less than 1. Is it possible? That we do not know. We have to see it after we get the derived equation through the algebra. Okay. But how do we proceed with this question? So, here I am going to apply the concepts of solutions of triangle or properties of triangle. So, how do I do that? I will take this side as small b, I will take this side as small a. And because a and b were not given in the question, these are supposed to be variables. A and b are varying because the point C is varying. Now, how do we get tan A by 2, tan B by 2? Do you remember any formulae? Of course, you need to remember tan A by 2 can be written this way, root of s minus b into s minus c by s into s minus a, or we can also write this as delta by s into s minus a, right? Or you can also represent that in terms of the in radius. Okay. So, if we use in radius here, it will be r by s minus a. Any one of them you can use, it does not matter. But we try to avoid the terms with square roots because algebra will be little complicated. Now, we know tan A by 2. In similar manner, we can also get tan B by 2. So, let us say I take the delta version, you can take any version you want. Okay. Now, the ratio of these two is given as constant k. So, that means I can say that tan A by 2 by tan B by 2 must be equal to, what do I get here? S minus A by S minus B. Okay. Now, that means this constant k must be equal to S minus A by S minus B, it must be equal to k, right. Now what is the next step? We know that both A and B are variables, and of course S also will vary because C point is varying, but still we can get a relation here by taking componendo and dividendo. Suppose let us say I take the componendo dividendo. So what do I get? This is in the numerator and this is in the denominator, and this must be equal to k minus 1 by k plus 1, right? Sorry, k plus 1 by k minus 1. Further, if you notice the numerator, it is 2s minus a plus b, and the denominator is basically b minus a, and it is going to give us k plus 1 by k minus 1. Okay. So now here if you notice, what happens when k is equal to 1? When k is equal to 1, a becomes equal to b. When a becomes equal to b, then that means c is on the perpendicular bisector. Okay. So let us just evaluate this first and then discuss it later. Okay. Now here we know that the 2s is going to be a plus b plus c. So 2s minus a plus b is going to be c. So which means I can use the constant c in the numerator here. So I'll get c by b minus a is equal to k plus 1 by k minus 1. Now this means I can say that b minus a is going to be k minus 1 by k plus 1 into c. Now here out of these two, b and a, we do not know which is bigger, which is smaller. Okay. So if a is bigger than b, then that means this LHS is negative. So that means RHS also must be somewhat negative. So when is it possible? K is anyways a positive number, but when k is less than 1, when k is smaller than 1, we may get negative value in RHS. Okay. So here you can take two cases. If a is greater than b, we may get the locus point somewhere here in the left side. So that means this ratio must be positive, and if a is greater than b, we will get locus point in the right side. That means ratio must be negative. Okay. So even if I just put mod here, that two sides will be balanced. If I put mod here, so I am basically considering both sides. Here also there is one locus point, here also there is one locus point. Both are varying. Okay. Now look at this condition. Can we say that it is going to be a hyperbola? This is going to be a hyperbola only if the RHS is less than the distance between AB. So PA minus PB must be less than AB. Okay. So this constant must be less than C. Is it possible here? Of course it is possible, because out of these k minus 1 and k plus 1 is bigger than k minus 1. So hence RHS is definitely less than C. Hence we can say that the locus of point C is a hyperbola. Okay. So here we can take those cases that you were confused with. One case was what happens when k is equal to 1. Second case was what happens when k is less than 1. What happens when k is greater than 1. Okay. So I discussed them in simple qualitative manner, but now I will explain them completely with the diagram. Okay. If k is equal to 1, what do we get? If k is equal to 1, that means tan a by 2 is equal to tan b by 2. That means a and b are equal. If a and b are equal, that means these two angles are equal. So that means locus of C is going to be a perpendicular bisector. Now if k is less than 1, that means which is less than 1? K is less than 1 means tan a by 2 is smaller than tan b by 2. That means this angle is smaller than this angle. So the point is in the right side. So we may get one branch of hyperbola here. If k is greater than 1, we may get another branch of hyperbola here. Okay. And if k is equal to 1, we are going to get the perpendicular bisector. Okay. Now based on the value of k, this branch may vary. They may come closer or they may move farther. Basically the value of eccentricity will depend on the value of k. Okay. So this way we can solve the problem and also we can analyze qualitatively. Okay. So come on, make a note of this. Okay, we will move on to the next question now. From 1 comma b, exactly 2 tangents can be drawn to this curve. Find the range of b. How do we solve this? Because we don't know for sure whether the point is on the curve or outside the curve, but it is given that 2 tangents must be drawn, so point must be outside. So what is the method to find the tangents through a point which is external to the curve? There are two methods. One is the POSL form, combined form, SS11 equal to S1 square, or the separate form. That will start with the slope form of the tangent. So let me use that method here. So if I use the slope form, what is the slope form of the tangent of this curve? Y equal to mx plus minus root of b square m square minus, sorry, a square m square minus b square, right? Now we are going to substitute the point 1 comma b in this. So what do we get? If I put 1 here and b here, I will get b minus m equal to plus minus root of 4m square minus 1. If I square this, so I get b minus m whole square equal to 4m square minus 1. Now I will extract all coefficients because this is going to be a quadratic. So when I take m square common, so there is 1 m square here, 4m square here, so I will take everything to RHS. So here I will get 3 plus m, if I take common, I am going to get 2ab term here, so that will give me 2b, and the constant which is minus 1 minus b square, which is equal to 0. This is quadratic equation. Because the point is external, so I should be getting 2 tangents. 2 tangents means the values of m here that I can get after solving must be real and distinct. So that means delta must be greater than 0. So this will give me required values of b for this situation. So what will be the discriminant here? It is going to be 2b whole square minus 4 into 3 into minus 1 minus b square, it must be greater than 0. Now if I simplify this, I will get 4 common, and there is 3b square here, 1b square here, 4b square plus 3 greater than 0. If you look at this inequality, because LHS is already a positive quantity, so values of b can be any real number. So that means b must be belonging to all real values. So what are the values of b? All real values are possible. Now can we not do this directly using geometry? Of course we can attempt. So let me just draw the curve and explain it to you. Suppose let us say there is this hyperbola, okay. Now this point is going to be 2 comma 0, this is minus 2 comma 0, this is the center which is 0 0, okay. And the point 1 comma b has one coordinate fixed, x coordinate is fixed but y coordinate is varying. So that means we can write x equal to 1 as the equation of this variable point. It is going to be a straight line. So that means through 1 comma 0, if I draw one vertical line, so my point 1 comma b is on this line. Now check the location of this line with respect to the curve. Is there any point on the line which is interior to the curve? No point. Is there any point which is on the curve? No. So that means through any point on this red line, I can of course draw tangents, because through any external point we can draw tangents, okay. So that means all real values of b must be the solutions, because we are able to draw tangents from any point on this line. Now you may get one slight confusion if you think about it, because we have asymptotes here. Now this line cuts the asymptotes at 2 points p and q. So you might be wondering what would be the tangents through these 2 points. So let us analyze for the entire region here to develop even micro understanding, okay. So from any point between p and q, from any point between P and Q, if I draw tangents, I can draw two tangents to only this branch, but not to this branch. This discussion I have done in the first lecture. And from P and Q, if we draw tangents, one of the tangents will be the asymptotes only, and the other tangent will be touching hyperbola at some point. So, here also tangents are possible, but only thing is one tangent becomes the asymptote only. But for any point on this part, we can always draw two tangents, one to each branch. Similarly, from this region, we can draw one tangent each to these two branches. So, this way also we can solve it geometrically. So, please remember that if you are able to check the solution using geometry, you have actually killed the problem using geometry only. Okay. So, please be alert when you are solving the questions. Okay. Come on, make a note of this. Now, let us move to the rectangular hyperbola. Okay. So, we have very less time left, we will try to finish as much as possible. So, here xy equal to c square is the standard form of rectangular hyperbola. We have learned all the basics that transverse axis is going to be equal to conjugate axis and eccentricity is going to be equal to root 2. Transverse conjugate axes are also equal to the latus rectum. You have learned all of them. And if it is in the first and third quadrants, xy equal to c square is the equation. If it is in second and fourth quadrants, xy equal to minus c square is the equation. And any point in this on this curve can be written as Ct c by t. Now, any point on this curve can be written as minus Ct comma c by t. Now, you can also put the minus sign on y and put plus sign on x, it does not matter, because t is the parameter which is going to take care of the sign. Okay. So, these are basic ideas, and also the transverse axis of this curve is going to be the line y equal to x line, conjugate axis of this curve is going to be the line y equal to minus x line. Okay. Now, using these ideas you can generate all characteristics of this curve. Okay. So, let us generate all characteristics. Center is going to be origin, and how do we find vertices? Let us look at this diagram. Now, we have observed that the transverse axis is going to be basically y equal to x line. So, if I solve xy equal to c square with this line, I am going to get the vertices. So, we know that on this line y equal to x is always satisfied. So, if I put y equal to x, I will get x and y to be c and c. So, this point is going to be c comma c, and similarly this point is going to be minus c comma minus c. Okay. So, we got the vertices. Now, can we write plus minus c comma plus minus c here? No, of course not. We do this only when both plus minus are allowed. So, if I am writing it this way, then that means I am actually writing 4 points there, because there are 2 possibilities each for both x and y. So, instead of that, we should be writing c comma c and minus c comma minus c. Okay. Next, what are the foci? We know that the value of a here is the distance of the vertex from the center. So, what is the distance of this point from here? It is going to be c root 2. So, if the a is c root 2 and we know that the value of eccentricity is basically root 2 only. So, what will be AE? It will be 2c. So, that means the focus can be calculated by taking the distance to be AE. Now, because both x and y coordinates are to be equal, so if I take one as h, other also will be h, 2h square must be equal to the 4c square. So, that way we can get h. So, this is going to be c root 2 comma c root 2. Similarly, we can also find the foot of the directrix. How do we do that? By applying the same idea, but here we need a by e. A by e is going to be c root 2 by root 2, which is same as c. So, this point will be c by root 2 comma c by root 2, right. Now, we can also get the equation of directrix directly. How do we do that? Because the slope of this line, which is the conjugate axis, will be same as the directrix. Conjugate axis is basically y plus x equal to 0. So, this will be x plus y equal to some constant k. How do we get the constant? I keep repeating the same idea. Put the point in LHS, you get the RHS. Okay. So, c by root 2 plus c by root 2 will give you c root 2. That becomes our directrix. So, here what have we done? We found the foci, directrices. Now, length of transverse axis is going to be 2a, which is 2c root 2. Similarly, conjugate axis is also 2c root 2. Eccentricity is root 2. Latus rectum is 2c root 2. Ends of latera recta, okay, before that, what is the auxiliary circle? X square plus y square is going to be equal to a square. A is c root 2, so it is 2c square. And similarly, parametric form, this we have already learned, ct, c by t. Now, we just have to find ends of latera recta. So, how do we find ends of latera recta? To find ends of latera recta, we have to find the points where this line cuts the curve. So, how do we do that? We can get the equation and solve it, but that is going to be long, but we can use the parametric form, because we know that this length is going to be equal to a, because latus rectum is equal to 2a. So, we have to move in this direction for a units. Now, what is the slope of this line? Slope of this line is basically tan theta, which is -1. So, we can write, let us say if I take this point as L, this as L dash. So, we can write L as c root 2 plus a cos theta, comma c root 2 plus a sin theta. And we know that a is basically c root 2, and here also we know that a is basically c root 2, but I have not put cos theta and sin theta here. Now, how do we apply that cos theta sin theta idea here? If you start from this point and if you are going in this direction, even though your point is in the first quadrant, because your direction is ending or it is approaching the second quadrant, this direction is towards the second quadrant. So, in second quadrant, you know that sin theta and cos theta, out of these two, sin theta is positive and cos theta is negative. So, use that idea to find the and generate the values of cos theta and sin theta, because tan theta is -1. So, cos theta and sin theta will have magnitudes 1 by root 2 only, but one of them is going to carry negative sign. Which is the negative sign? For that you use this direction idea. If you are moving along a direction which is going to end in the second quadrant, even though your point is in the first quadrant, if the direction is towards second quadrant, take sin theta positive, cos theta negative. So, this is going to be -1 by root 2 and this is going to be 1 by root 2. So, with this we can write c into root 2 minus 1, comma c into root 2 plus 1 as the ends of this one end of the lattice rectum. Now, the other end can be calculated in similar manner, okay. But if you are going in this direction, because that direction is towards the fourth quadrant, in fourth quadrant sin theta must be negative, cos theta must be positive. So, using these ideas we can write the ends of latera recta as c into root 2 plus minus 1, comma c into root 2 plus minus 1. There are 4 points here, that is why I wrote plus minus here, okay. So, this way we can solve the problem. We can also write all characteristics, okay. So, try to complete this on your own. We will meet again in the next lecture and we will take it from there and we will move on, okay. So, I hope you enjoyed today's lecture. We will meet again in the next lecture. Until then, have a great learning day. Learning shall never stop.